Guys, I think it's time to start. About 3 p.m. So, hopefully this is the last lecture about refreshing concepts, and next time we'll start seeing the gravitational law and Keplerian orbits. A few things I want to highlight. I made sure this thing of the video is doable. I can do it. The only thing is I need to ask you guys, don't walk in front of the camera. There are some privacy issues, and I don't want to get into any kind of trouble. So if you start being in the videos, I can't post them. That's the only thing I need to ask you. And I don't think anyone will ever go in front, but just so that you know. You can wear a mask if you want. In that case, you can be in front of the camera. But I also wanted to tell you I have a very basic Facebook page for the lab called Adamos, if you're interested. I'm going to try to make it a little more interesting for the future, so check it out. One thing that I also have to highlight, when we talked about reference frames and coordinate systems, one thing we want to make sure we all understand is that a coordinate system must be fixed, I think we said that more or less, in only one reference frame. Okay? Oh, what's wrong with these things? If this is my reference frame, the board, I can have infinite coordinate systems that I can choose. I can choose any origin here, infinite points, infinite combination of directions. But once you pick one, you're stuck with that, and that doesn't change. It's fixed with the board. So you have infinite possible coordinate systems in a reference frame, but a coordinate system is only fixed in one reference frame. Make sense? Nothing special. I want to finish that problem we were rushing to do last time, which is really of no interest for an astro class, but it is of interest just to highlight why the transport theorem is so important. Okay, so we said we have ground here. We have a particle P. We're still doing kinematics. I don't have to talk about masses, as I will do in a few minutes. So that's really just a point that is free to move inside this pipe. And we call this angle theta. And we wanted to find the velocity of P with respect to the ground. That's my unknown. And possibly the acceleration. Why not? So 2 time derivatives of vectors here. And we said the steps are that, first of all, you set your reference frames. Don't even think about doing any dynamics if you don't know what your reference frames are. Doesn't make any sense. Who is the observer? You need to state that clearly. So you start with the reference frames, and we said, okay, one is the ground, it's there. And the other one is, I called it A, this object here. So I hope we understand at this point the reference frames are really objects in most of the cases. In reality, that's what they are. Objects that are more or less rigid objects. So in this case, the pipe can be one. I can easily find 3 points that define my ground, and I can find 3 points on this pipe here that give me another reference frame. So those are the two, and you need to spell them out. Then you need to choose the coordinate systems. And we observe that point O is fixed in both, right? We said that. Origin at O for G and A. So, and then what I would do in a classical dynamics class, I would go along defining very pedantically the directions for the 2 bases. Here I need 2 coordinate systems. I have 2 reference frames. So for the ground, I would say that, so you will have it on video. I'm not going to write it down, but you can always go back to this video. I would say that, for example, the direction EX is the direction OP when theta is 0. Then I can say that I have a direction EZ that is sticking out of the page, and then the EY that completes my right-handed orthonormal basis. That's fine. And then I need the coordinate system. This was for A, so this is fixed in A. And then I need the one that is fixed in, G, right? And then I need the one that is fixed in A. I said some EX direction that is along OA for any theta, so it goes with the rotating tube here. I recycle big EZ, so I have a little EZ up here and little EY. Rule of thumb is, as I said last time, you have one rotation that involves two reference frames. It should be pretty obvious. If you talk about a rotation, there is someone looking at something else rotating. So that someone and that something else are your two reference frames, And then each rotation you add another one. And it's a good idea to recycle points when you can. So the same origin in this case, it's a good idea to recycle axes when you can. EZ and big EZ, a little EZ can be the same axis. These are not things that you must do. These are just good ideas. You can come up with whatever you want. You can, again, have coordinate systems that don't have the axis at 90 degrees and have weird angles all over the place if you want to make your life very complicated. So these are not things that you must do. These are things that make sense. And we said last time, okay, this distance, we call it r, little r. And what is the velocity? Is the rate of change of a position. So this is, by definition, the d dt taken by the observer fixed in g of the position of the particle, rp. And we said that rp can be expressed in two different ways, since I have two coordinate systems here. The first one we explored was r cos theta big Ex plus r sine theta big Ey. But this is also equal to just r Ex. Agree? So this is a clear example. This is the same vector. I just write it in two different languages. And so the first, if I take the rate of change of the first one, my velocity of p in g is, we said, minus r theta dot sine of theta Ex plus r theta dot cosine of theta Ey. And if you want the acceleration, we do it again. And I'm not going to do it. The second way, so alternative way, I don't remember if I got to this point, I probably did, is to say that Vp in g being the rate of change of the position of the particle in g, thanks to the transport theorem, is the rate of change in A of the same vector plus the angular velocity of reference frame A with respect to the ground crossed with Rp itself. Now, if it's now the observer A that takes the rate of change of this vector that goes from O to P, it's probably looking at this expression down there, and the only thing that this guy sees is r dot little Ex plus the angular velocity of A with respect to G. As I said, you can always bring down 3D rotations into single axis rotation, so this is a single axis rotation, is given the sign of the directions I've chosen is theta dot little Ez cross with r little Ex. Okay? Question before I move on? Very simple cross product. Can I do this? They are the same vector, right? That's the first question. Then I'll ask you another question later on. So, and this is just pretty straightforward. R dot Ex plus r theta dot Ey. Now you prove to yourself that this and these are the same thing. They are the same vector, the velocity of p in g. You can do your basis transformation if you want. So what's the benefit of doing this? Well, for a problem that simple, not a huge benefit. But I do have something else to say here, and that is that this gives me some insight. I can visualize this. So when you see a particle moving, depending on in which direction it's moving, you can have an idea for the direction of the velocity vector. So that particle can only move in two ways if you want to decompose. If I lock in place A, it's moving radially, and that's your radial velocity, r dot Ex, right? But then this is free to rotate, and that's your tangential velocity, r theta dot Ey. I can understand those. No? Radial, tangential. It's a combination of two motions. I cannot understand this, quite frankly. That r theta dot cosine. And then you go on with more complicated problems. It becomes even worse. So the transport theorem is not only a means to use when you don't want to write vectors and take huge derivatives. It's also something that gives you a little more insight in terms of the results. So as I will go on with the classes here, I will here and there tell you, you do this at home. You finish this at home. Yes?
Is the first derivative r constant?
No. You're right. That's an error. That's a good point. R is not constant. What is missing here? What is missing? That makes it even worse. So that supports my, my cause, I guess. So this, thank you. This was, I was basically doing a pendulum almost. These two are the derivatives when I look at theta, and then I have this extra term, right? Why? Thank you. Anything else? So, as I was saying, I will throw in there several, you finish this at home. So one thing you want to finish at home is prove to yourself that these two vectors are the same. Quite frankly, this should be equivalent to the r dot ex, and the rest should give you this, of course. And also do the acceleration. How would you do the acceleration with the transport theorem, by the way? Ideas? Well, this is another rate of change with respect to the ground of the velocity of p with respect to the ground, right? I have two expressions for the velocity, a super ugly one to which we added even more stuff because it was missing, and this one. Which one do you want to use? Probably the second one. So if I want to use the second one, which is expressed in a basis fixed in A, then you do the transport theorem again. D dt in A of this whole thing, which is Vp in G, plus another omega A G cross with Vp in G. You think you can do this yourself? So we can move on. The first term, the rate of change of this vector here, this first rate of change, you change r, so this will become an r double dot, not little ex, not little ey, because you are in A, and then this term will give you an r dot theta dot plus r theta double dot, and then you do the cross product. Try to do it in both ways and see which one you like the best. Now the question that I usually would get at this point is, okay, you've done this problem where the origin is the same. What happens if it's not the same, right? Nothing, really. As a matter of fact, I haven't demonstrated the transport theorem to you, but the demonstration does not make any assumptions at all in terms of the reference frames involved and the coordinate systems. They don't have to share the same origin. So I'm going to apply the transport theorem a few times here with a lot of symbolic calculation because I want to derive this expression that we're going to use next time as we start talking about Keplerian orbits. So let's say that now we have a generic case where I have, again, a reference frame A and a reference frame B and their respective defined coordinate system. So the origin of this coordinate system is O, which is fixed in A, and here let's call it O prime, which is fixed in B. Okay, and P, it's the point that I'm looking at. And so I have two observers here, right? Let me call the vector OP just R. Of course, it's not going to P. Okay, I'll call this R. And my interest will be to see how the observer A sees P moving, velocity and acceleration. And then I have the vector goes from O prime to P, let's just call it RP with respect to O prime, and then I'm terrible at connecting dots. This is the position of O prime. So I want to know what AC is here, but I probably have some measurements in B. Okay, let's see what happens. Nothing special. R is going to be equal to RO prime plus RP with respect to O prime. Just a triangle right there, right? 3 vectors. The velocity of P with respect to A is the rate of change of this, rate of change with respect to A of R, which is the rate of change with respect to A of RO prime plus the rate of change with respect to A of RPO prime. Okay, what is this? What is the rate of change with respect to A of RO prime? I am sitting down here, and I see O prime moving. That's the velocity of O prime with respect to A, right? Then this vector here, RPO prime, well, if I'm sitting here, if the other guy sits here and is probably measuring this vector, that is something that is probably expressed in a basis fixed in B. So I'm going to use a transport theorem right there, which tells me that I can do d dt. We're going to get something that you have seen several times. You probably don't know that it comes from here, or maybe you do, I don't know. I'm going to apply the transport theorem to this vector here. What is this? What do you call that? What is the d dt in B of RPO prime? I am now, these are the guys sitting here, and I'm measuring from this point where that point is, and I have a vector, and I take its rate of change. What is that? It's a velocity. It's the velocity of P seen by the observer B plus that term. So that's the first result that I'm going to write here. The observer A sees the velocity of that particle and it can be also expressed as the velocity seen by the observer B plus this extra term here that is basically taking into account the rototranslational motion of the reference frame B, right? That's what this gives me. That piece is there because B is moving. Make sense? If you drive this to 0, the origin of B, the origin fixed in B doesn't move with respect to A, and if there is no rotation, this goes to 0. So this extra term is due to the motion of reference frame B. I'm sure you've seen this expression all over the place. No? Yes? You forgot? Okay, we're going to use this next time. This is really my end of kinematics. Can I erase this? No. Okay, too late. I can almost save it. Yeah, I think I can save it. Is that what it was? I think so. Let's move here. I have to do the same for the acceleration. So for the acceleration, we're going to get all those pretty famous terms that people call Coriolis acceleration and centripetal acceleration, and I don't know if the other pieces have any names. You can call them whatever they want. They are just vectors that arise from the fact that I am involved in 2 reference frames instead of 1, and they move with respect to each other. They translate and rotate with respect to each other. So I'm going to take this and do it again. The acceleration of P with respect to A is nothing else than the rate of change with respect to A of that vector Vp with respect to A, which is expressed as that right-hand side. So what do I have? I have, let me rearrange things a little bit. I have d dt in A of VO prime in A. For this one, I don't want to do anything. I don't need transport theorem. Then I would have the rate of change in A of velocity of p seen by b. For this, I will use transport theorem. And then rate of change in A of omega b with respect to A crossed with rp O prime. See, I'm not skipping, I try not to skip steps. I know that a velocity is a rate of change, but I write down the d dt with respect to who at least once, because I already make mistakes by myself, as you've noticed before. So if I start skipping steps, I make even more. Okay, what is this? If I have the velocity of this point, O prime, that is measured by A, and that same guy A takes the rate of change of that vector, what does it measure? Acceleration of O prime with respect to A. Done. That doesn't change. This I'm going to use the transport theorem because this is the velocity that B sees. So probably that vector is expressed in a basis in B. So that becomes d dt in B. We just keep applying the transport theorem. There's really nothing else that we do here. Plus omega b A crossed with the velocity of p in B. Do you remember what happens to the angular velocity when you take its rate of change? There was a property that it doesn't matter who does it, right? We didn't prove it, but it's easy to prove. If you want, I can do it in office hours. So the rate of change with respect to A or any reference frame of this vector is just alpha b with respect to A. Angular acceleration of b with respect to A crossed with rp O prime. And then I have omega b A, which is crossing the rate of change with respect to A of rp O prime. Let's give a meaning to this vector here. This is what B sees. B is measuring the velocity of this point, and it's taking the rate of change of the vector. So that is the acceleration of P with respect to B. This vector, okay? I'm going to leave this as it is. Same with that. Transport theorem. Again, RPO prime is probably expressed in a basis in B. So I'm going to do that again. So that is omega B with respect to A, which is crossing what? What is that crossing? It's the rate of change with respect to B of RPO prime plus omega BA cross with RPO prime. You should be tired of this stuff already. Are you? Yeah? Okay, what is this? If you're not comfortable with responding to this quick, I do strongly suggest that you go back and revise your dynamics. This is the velocity, what? Of P respect to B. Right? And so finally we have acceleration of O prime with respect to A plus acceleration of P with respect to B plus twice omega B A cross with B P in B plus alpha B with respect to A cross with RP O prime plus this double cross product that remains as it is. And by the way, the order of these cross products does matter. You can't just do whatever you want. That's why I put a parenthesis here. Okay? And so this is also, of course, I started from there. This is the acceleration of P with respect to A. And I'm sure you've seen this multiple times. Have you seen it proven to you? Probably. Yes? Yeah? That's not a big deal. You don't really need to memorize this thing. Every time you have a problem, you use the transport theorem, as I've done multiple times, if you need to. You just need to know which vectors are expressed in which basis and when it makes sense to use the transport theorem. So this is probably what you call the Coriolis acceleration. I don't know if this has a name. If it does, I don't remember what it is. And this is the centripetal acceleration. This is the acceleration of a particle P seen by B. This is how the origin of the coordinate system fixed in B is moving with respect to A. So all this comes out from the fact that you do have two potentially moving reference frames involved. And this puts the end to the review of kinematics, as far as I'm concerned. I think that's enough. The one thing that you also have seen, probably, not if you're taking dynamics with Dr. Rao, is that why do we do all this craziness? Is because we want to do kinetics at some point and find equations of motion of systems. And so we need to be able to write F equal ma, right? And so that's the A part. You may have frames involved that are more than one, and you may be forced to use this expression. And so people write ma, say that the observer A is inertial, but they may actually have the acceleration of this particle expressed by this. And so they start doing the following. They start doing m acceleration of O prime in A plus m acceleration of P in B plus, and I'm going to stop here, 2m omega BA cross with BP in B plus the other terms. And they start saying, this is the Coriolis force. Okay? You've seen this, right? Centripetal force, Coriolis force, whatever force. These are not forces. This is not true. The forces are on the left-hand side of this equation and are things that are due to action that is actually exerted on your particle. This is just you deciding that it was convenient to use some B reference frame that is probably non-inertial, and I have to define what inertial means, but basically you decided at some point to use more than one reference frame, and you have all this expression for the acceleration of P. But that was your choice. You can't call this a force. This is not a force. This is a mass times an acceleration. You're just using a basis that is probably rotating and translating. Make sense? So you can keep calling them that way, but I usually don't, because they're not forces. They're not generated by attraction, by something pushing on your particle. They are not forces. So it's time to talk about forces. Any questions? No questions? Kinetics. Promise that we're going to start talking about interesting stuff next time. But this, we'll use it next time. OK, so to do kinetics, we need a few things. What do we need? A few concepts. Same way for kinematics, you start talking about position, then velocity, then acceleration, reference frames, coordinate systems, all that stuff. I need, number one, mass. Remember, we're doing particles. One particle. Our satellite would be a particle going around the planet for most of the semester. So we need to start talking about mass, the quantity of matter that is associated with this particle. Otherwise, there is no physics to the problem. There is only points that move around, and you can't really apply any forces to them. So the second is action, what we call forces or torques, if we have rigid bodies. And these are vectors as well, right? We represent, same way we represent positions, velocities, accelerations with vectors, we represent actions with forces. What else do we need? Newton gave us 3 laws, but they work only under certain conditions. Inertial reference frame. We need this concept of inertial reference frame. Inertial reference. Now, frame or frames. A law is something that is given to us and it's true until someone proves it wrong. So we don't demonstrate a law. In fact, Newton's laws are false if you're moving close to the speed of light, but as far as we are concerned, as we said, they're fine. And so we accept them and use them. What is an inertial reference frame? No one knows. Right. The definition of inertial reference frame is kind of it's a circular definition. Inertial reference frames don't really exist, but we assume that there is a set of at least the usual definition, 3 non-collinear points, at least 3 non-collinear points at, let me just say, fixed mutual distances. That are what? They need to be absolutely stationary. You see the contradiction here? Motion is relative, as far as we know. Absolutely stationary with respect to what? But that's one of the definitions you will find. And we accept it. My addition to this is, you can imagine there is a creator somewhere, the source of life, that sees everything and can decide, yes, that's an inertial reference frame. You can see it that way. That's the way I see it. But they don't really exist. The reality is that the laws of Newton, as we'll list them in a second, are valid in inertial reference frame. So another definition you can give is an inertial reference frame is one where the laws of Newton apply. It's a circular definition. They don't really exist. But we use a lot of reference frames that are non-inertial in reality that are good enough for our experiments because the laws that I'm going to give you, that you know already, do work fine. So that's what we do as engineers. We approximate reality, right? And the first one that we use, and we use it all the time, is this planet, right? What do? We say, okay, we pick center of the Earth. The Earth, we basically, pick center of the Earth as one of the points for my reference frame. 2 more points that are some faraway stars that seem, appear not to move at all, even during a year, and we point axes in those directions, and we say that's the coordinate system associated with my reference frame, right? And we say that this, called usually ECI, Earth-centered inertial reference frame, we say that this is inertial. Oh, by the way, usually the letter that you find in textbooks for inertial frames is N. Now, we do know that this is not inertial. That point, the center of this planet, is not absolutely stationary. It's going around the sun, right? But it's good enough. It moves. So the directions, I can keep them fixed. So I can drive the omega to 0 with respect to some external observer. But the center of the planet is not stationary. It's actually accelerating. It's moving in some elliptical orbit. So there is an acceleration there. But it takes a year to go around, and it may be negligible to some extent. Maybe small enough that you don't care. That's what we always do. We neglect stuff. Now, an additional comment to this is that any reference frame translating at constant velocity with respect to, let's say, n, so that is the absolutely stationary points, is also inertial, which is great because you don't need just one absolute inertial reference frame. You can have infinite of them as long as they translate at constant velocity with respect to each other. No changes in orientation, just translation. Yes?
Isn't it any 3 points that don't have forces acting upon them?
Yes.
Is that a...
But I can put an object in space in rotation, initial rotation, then I don't touch it. There's no forces on that object. That object keeps rotating. That is not inertial. So it depends. It depends on your initial conditions, and those initial conditions go back to the origin of the universe, pretty much. If you have something that is rotating with respect to what, we don't know. But if there is rotation, you're also not inertial. So, but basically we assume that the planet is inertial to some extent, and anything that translates at constant velocity is inertial. So in inertial reference frames, these three laws are valid. That's really all we care about. Okay? One, it's the inertial law. I'm not going to write it down. Tells us that an object remains at rest, tends to remain at rest, or to move at constant velocity if you don't have any action on that object, right? Keeps doing whatever it's doing if you leave it alone. Then the very important one from which we derive equations of motion, F equal ma. Finally, I can write this and give it some meaning. The resultant of all forces acting on a particle of mass m is equal to the product of the mass of the particle and the acceleration of that particle measured by an inertial observer. And again, one infinite inertial observers, as long as they translate with respect to each other, it's okay. You get the same acceleration. 3, action reaction, right? If I have a particle 1 and a particle 2 of different masses and 2 acts on 1 with a force that we call F1 given by 2, then 2 will receive a force that is exactly the opposite. And you have to have a minus in front. Okay? Now this is what is called the strong form of the action-reaction principle. In reality, you have cases where this happens, and this is fine too, where the two forces are not on the same line of action, but it's mostly due to electromagnetic forces. We're not going to see any of that probably. So those are the three. You want a problem, just to refresh our dynamics skills here. Redo the problem I gave you and add gravity. For example, do this. Now this particle now has some mass, of course, and there is gravity. So this is one of the few times that we're going to do this vector that points down and it's constant, because definitely it's not something you want to do in an astrodynamics class. You know how many assumptions go behind this? Any idea? As long as you don't walk in front of the camera, you can talk, I think. Well, we say that G is constant, right? Some 9.81 meters per second square pointing down. There is the assumption that this is a big one. Right? That's the first one. That's what we always make. So that's what you do when you have problems like this. The Earth is flat. The gravity doesn't change with height. Of course, there is no height if it's flat, pretty much. But that's, there is a lot of approximations that we make, even when we start next time to look at Keplerian orbits. We'll make up models for forces that don't really represent reality. You have any questions up to this point? Again, this was just refreshing things that we're going to use starting next time. The additional refresher I want to give you, because you're going to be really fed up with it, so we need to see it. It's the following. This is going to be with us for the entire semester. Angular momentum. Do we remember the definition of angular? This is still a particle again. It's doing particles, single particles. I have a particle of mass m in three-dimensional Euclidean space, and I define at another point q, which is any. Doesn't have to have a mass. It's just a point. the angular momentum with respect to the point Q, with respect to the inertial frame, as position of the particle minus position of the point that I've chosen crossed with m, velocity of the particle, with respect to n, minus velocity of q with respect to n. Q is any, p is a particle mass m, and this is the angular momentum with respect to that point q. The superscript n is there because I use velocities here that are computed by, with respect to an inertial observer. And without proving anything, there is a derived result that originates from Newton's laws. So this is not a law. This is just something that you can derive from F equal ma. The rate of change in n of this vector is equal to the moment of all forces with respect to q that act on the particle minus rp minus rq cross with m a q in n. We're going to use this stuff quite a bit. Do you remember this? Again, this is not a law. This is not, you can't say that this is at the same level of F or F equal ma. That's a law. This comes from that. You can demonstrate this expression. It's not just given to you. You can get to this result here. And what else do I want to give you? Well, what is mq? Just to be thorough here, it's the moment of all forces on the particle with respect to u. So mq is rp minus rq cross with f. That's it. And of course, if the acceleration of the point q that you have chosen is 0, well, you're just left with these two pieces, which is not always necessarily a good idea. Okay. I think with the time we have, we start just wrapping up kinematics and kinetics, just solving a problem. If you want the same we had before, maybe the usual pendulum. And then I'm going to give you something you can play with at home as an uncollected homework. Usual pendulum. I know this stuff is obvious, but I don't care. I'm refreshing dynamics, and I want everybody to be on the same page. So now there is a mass. This is a massless rod, and I call theta my parameter here. And I say that the ground, I'm going to call G, but I say that this is inertial as well. See, all this stuff, we do that all the time when we solve problems. The moment you start writing F equal ma, and you compute that acceleration with respect to some reference frame, you are assuming that that frame is inertial. You don't say it, but that's what you do. There's a lot of assumptions you make when you solve problems. You just jump to the conclusion, you start writing equations, but you need to remember what's behind what you use. And even though this is a simple pendulum, I have chosen theta for you. I've already given you the parameter that you're going to use. Many problems you're not given that. So how do you find the equations of motion? What do you need to do? I'm going to do it with F equal ma, or at least start it, and then you at home do it with this. This is an alternative to F equal ma. Okay? Try to solve it with this. Should be really straightforward, and you should get the same equation. Well, before you attack a problem, it's a good idea to think about what it is that you're going to get. Visualize the goal before you go. Right? If you run a marathon, it's 26.2 miles. Think about that. You don't start running like crazy at the beginning because you're not going to finish. So have in mind where it is that you're going. What does this mean? What do you need to get? Before I even write reference frames and coordinate systems, what do you need to get? You need to see differential equations, so you need to see something that has theta, because that's the parameter I've given you, with its first and second time derivative, no more than that probably. And that's what I want. I want a differential equation or equations. So that's the second question. How many? Because in general, I will always ask you for a problem, write the equations of motion, because a problem may have more than one differential equation. How many do I expect here? It's pretty easy. It's 1. I gave you the parameter. It's right there. But you need to be convinced that it's 1, because this object is constrained to move in a plane. And in a plane, a particle has how many degrees of freedom? 2, x and y. But I am forcing it to rotate about this point here. Oh, that removes 1 degree of freedom. It's 1. That's your angle theta. So you expect 1 equation of motion. All this process should go right before you start writing anything on your paper. So we'll do it like this. You guys at home do, or at least I'll start it. Solve it this way. Solve it also with an additional degree of freedom. Allow this to rotate about the vertical axis with an angle beta. 2 rotations. It's going to be interesting. I want to see how many show up at office hours with questions. Yes? No. Beta is another variable. So now I'm giving you 2 degrees of freedom. You can give it a spin about the vertical axis initially, and that's what it is. Yes?
Beta is a hinge.
So it's this axis here, right? It's basically a rotation of the plane that contains the pendulum about the g direction. Make sense? So if this is the g direction, it's a real it's a 3-dimensional pendulum. How many have seen the Foucault pendulum in reality? That's what it is. It's it's a pendulum in real space. It can go in 2 directions, right? Try to do it that way, but I'm not going to do it that way. Not today. So what do? I know that I expect 1 equation of motion, because for now I'm not going to have beta. But this is a good exercise for you to refresh dynamics in general. I have the reference frames like before, ground, and let's call this A again. Now this is an abuse. This is a line, right? Can I call that a reference frame? Not really. On a line I can't get 3 non-collinear points, but I can choose O, I can choose P, and then a third point that it's away from that line that remains a constant distance from the 2. And imagine this triangle, and that triangle goes up and down with OP. We can do that. As long as you know your assumptions. Coordinate systems, don't let me do it again. O is something that I can recycle for both. And I'm going to do EX, EY, EZ, as before. Wow, 50 minutes go fast. EZ, EY, that's fixed to the ground. And then, as before, EX, EZ, and EY this way. Nothing special. And so, done. Coordinate systems are done. So what do you need to do? You need to be able to write this. F equal ma with respect to the ground. The ground is inertial, so I can do this. So I start taking the derivative of what? Of my vector position that is given by, for example, r ex. Now going back to that great comment before, now r is constant. I was doing a pendulum. In my mind, I was doing a pendulum. So r or L, whatever you want to call this length, from O to P, down here, okay? Well, then it's easy. Velocity of P with respect to the ground, I'm going to skip the transport theorem right away and tell you that that should be r theta dot EY. There is only the tangential component. That particle is not allowed to go radially, right? So it's what I had before, except the r dot is not there anymore. The acceleration of P with respect to G is the rate of change of this, and I'm going to use the transport theorem again. R is constant, so this is going to give me r theta double dot EY. So this will be the rate of change of this vector with respect to A. And then the other one should give me something like r theta dot squared EX. And I'm going by memory, but this will be given by omega A with respect to G crossed with this vector. Makes sense. That's your acceleration. So you can write that m times that vector is equal to F. How do you model the forces? Free body diagram. Your particle is here, and there is mg, which you can express, given my axis, my basis, as m minus mg EY. And then there is some force that is exerted by the massless rod that we know is going to point to O only, call it the tension, whatever you want to call it, that it's unknown, and I can just write as T Ex. Another question I would get here, why don't you have a minus? Because I don't know if T is pointing with plus Ex or minus. In general, it can be in any direction. It's an unknown. It depends. If the pendulum is all the way up, you can actually push with Ex. And so you have to stick it in here. This is minus mg Ey plus T Ex. That's my F equal ma right there. Newton's second law. How do I get my equation of motion from this? Eliminate what you don't know, unless you need to solve for it. And what it is that you don't know, T. I don't like it. I'm going to dot everything with little ey. That takes away that piece. So I have m r theta double dot, little ey dot with little ey is what it is. This goes away. And then on the other side you have minus mg big Ey dotted with little ey. So all I am left to figure out is this dot product. What is it? I don't know. Some sine of theta, minus sine of theta, whatever that is. You guys do it. But this is your equation of motion. There are no unknowns left, right? Second order differential equation. This will be a sine of theta, cosine of theta, whatever that is, and I have solved the problem. So this is the stuff that we're going to use. Do resolve this problem with F equal ma adding the additional rotation. You need to figure out how the omega is going to change, and then resolve it with this. Okay? Thanks.